Dynamics, Control, Machine Learning, and Numerics at the Friedrich Alexander University of Erlangen-Nuremberg, where he has worked since 2019. He is an expert in PDEs, control theory, and machine learning, and is going to talk about the big role that machine learning is playing in the field of numerical PDEs and how it can complement traditional applied mathematics for the next hour. Please join me in welcoming Enrique Zuazua.
Thank you. Thank you. Good afternoon. Good afternoon. So yeah, as the chairman said, I was educated in Bilbao, in Basque Country, and then in Paris, so where I was at that time in this Jacques Louis-Lyon's laboratory, where we used to be trained in analysis, PDEs, numerical analysis, related topics like control optimization. So then in 2019, I came to Erlangen with a Humboldt chair. And then in Erlangen, I mean, it's a very nice university town. There is plenty of industry, like Siemens, Adidas, Schaeffler, all kind. And there is a lot of technological transfer between the university and all this rainbow of high-tech companies. But I realized that most of this was in the direction of artificial intelligence and machine learning, a topic that I didn't know about. And then COVID came, and we were isolated there with our group. And I said, well, why don't we try to learn a little bit about this? So actually, we started and we wrote a paper, long paper in Acta Numerica on the links between long time control and machine learning and deep learning. So we started by trying to recast a concept that is well known in classical control theory that is actually due to John von Neumann, right? So John von Neumann, in the context of game theory in economics, he had this intuition and he called the term turnpike. Well, I didn't know this word, so certainly Americans, you know what turnpike is, right? What is turnpike for you? It's a highway. Okay, so there is this turnpike principle by John von Neumann. So that actually I learned about, maybe it was like 2013 or so, we wrote an article with my colleague Alessio Porretta in Tor Vergara. You might know his name. He's a well-known expert in Hamilton, Jacobi, mean field equations, and so on. So we wrote an article in which we proved that for long time horizons, very often the control has the tendency to be a steady state, right? So, so what does it mean? It means that, well, if you give me a short time, and I have to understand, undertake some task in order to regulate, to control a system, I have to do it in a very complex manner, in a very oscillatory manner, probably even in a spiky manner. When there is an emergency, then you have to, use all your weapons in a Dirac delta kind of manner. But when the time horizon is very long, what von Neumann said is, listen, when the time horizon is very long, you can't just do it a steady state. Okay, so this is actually a principle that we all use in our lives. So maybe you don't know anything about control theory, but you don't need to know. You know that turnpike is the best path. So if you tell me that I have to go from here to the hotel and you give me 1 hour, I watch and I see, okay, I can just walk slowly. In 1 hour, I will be there. This is the turnpike. You don't need to run. You don't need to stop. You can just take a constant speed and you will be there. When you have a chronic disease, you go to the doctor and the doctor will tell you, take 1 tablet per day and come back in 6 months. So why 1 tablet per day? Our organism is not feeling the same way every day, especially when you are under jet lag and you get to sleep at 5 a.m. as it happened to me, last night, right? So you don't feel the same every day. So probably the optimal strategy for the doctor will be to say, listen, on Monday you take 1.01 tablets, and then on Tuesday you take 0.98, and then on Wednesday 0.97, and on Thursday 1.003. But this is very complicated to implement, right? So the doctor says, yes, one per week, one per day, and come back in 6 months. This is the long time horizon, steady state control that von Neumann realized it was applicable universally for every kind of purpose. It doesn't matter whether it's about transportation, finances, biomedicine, aeronautics. Actually, we wrote this paper because, I was trained in Paris, as I said. At that time, there was a lot of work ongoing on hyperbolic systems, numerics for hyperbolic systems, optimal shape design in aeronautics. There was a lot of cooperation with Airbus in particular. And whenever I would listen to a talk, I was very shocked that the optimal shape design for the airfoil was always built on the basis of steady state equations. So, how steady state? The airplane is, is moving so fast. We all know about, Navier-Stokes, turbulences. This is a genuinely dynamical problem. So why then, if the problem is genuinely dynamic, why the optimal shape design of this airfoil is done to a large extent on the basis of steady state models? Well, it's because of the Tarpike principle. You are designing the airplane in order to cross an ocean or intercontinentally for, say, 10,000 kilometers. And then when you travel intercontinental, basically you are evolving along a steady configuration. So we wrote that paper, but we didn't know the term Tarpike. We gave a complicated title to the paper, probably almost a quasi-static control for long time horizon problems. And one of the referees said, well, so did you have a look to Tarpike? And then I went to the Wikipedia and I opened Tarpike and I see a highway. What the referee is talking about? And then we recover all this. Well, so that was my introduction to the topic. Then I get to Erlangen, and I thought that maybe after reading a few papers on, machine learning, I said, well, maybe something we could do is try to explain the link between the different models in machine learning, some of them being static, some other ones being deep, right? And this is the topic of our paper with Borjan Geskowski in Acta Numerica. Okay, so we have been working on this for, say, 5 years or so. And then I wanted to give you my perspective to this topic, which is very, very, very limited, right? But I think is fundamentally true also, and can be very useful for all those interested, on applied mathematics in a broad sense. So I don't need to convince you that this is becoming now an important topic, artificial intelligence. You see it recognized in the, there is a delay of one, for some reason. I don't see the same on the screen and on the computer. Okay, here it is. So Nobel Prize in Physics and Chemistry last year was awarded to people working with or in artificial intelligence, protein design, and the fundamental contributions by Hinton to artificial intelligence. And for those that didn't follow these developments, well, you don't really need to know. You can just watch your telephone and you will see that it's already built in, right? So ChatGPT emerged, I don't know when it started, like maybe 3 years ago or so. And by now it's a revolution, right? It has been a revolution probably comparable to Google or to, search or to the email, right? So the young people maybe think that the email was invented, in prehistory, but no. 40 years ago, people working in academia were not using emails. They were probably using faxes or so instead, right? So Google search, internet, ChatGPT, all these have constituted revolutions, and that are changing the way we work, right? So the way we search in the internet has changed since ChatGPT arose. The way we translate letters, the way we draft bureaucratic letters now is much easier thanks to ChatGPT. You can just write, particular for me that I am in Germany and all the administration is done in German. My German is very elementary. So when I need a letter, well, I can ask ChatGPT, please write it in very high, German, a very long and detailed letter to explain why this PhD student deserves to, I don't know, a travel grant. Okay, very good. And then soon after, DeepSeek started. And we realized that DeepSeek came a bit later, but is doing, for free what ChatGPT basically, I mean, there are experts that will tell you, no, this is not totally true. ChatGPT is better than DeepSeek for that or for that, but basically for a standard user like me, DeepSeek does the same thing for free, right? And one of the reasons is that is this principle that we are walking on the shoulders of giants. So ChatGPT was a giant, and then based on this giant, you can build the next giant. Why? Because in principle, you can ask questions to ChatGPT. ChatGPT will give you answers, and this means that you are building new input-output pairs, so you can enrich your data set on which you are training, you are learning, and therefore you are building a monster that is smarter than the previous one. Okay? Very good. So, well, that's simply to say artificial intelligence is part of our lives, and this will stay, this will remain. Now, as a mathematician, what can you do? Well, you can just become a user, or you can also try to figure out, well, is there something in my field that is related to this, incredible success of artificial intelligence? Is artificial intelligence something that emerged out of computer science, maybe, in which my math field has nothing to do? Or maybe if I open the box of artificial intelligence, I will find that this is fundamentally rooted in some of the principles that actually constitute some of our fields in in applied mathematics. Let's see. So looking from closer and doing some simulations, this is what I found. So this is a simulation we did a few years ago with a postdoc, Kong from Korea. This was control theory. 4 dogs herding a flock of sheep. Classical control theory. 4 dogs in blue, hundreds of sheep. Dogs start dancing, right? Sheep don't know what they are doing. They are simply afraid of these 4 dogs that are surrounding them. Sheep try to be together on one hand. There is a lot of viscosity that keeps them together. On the other hand, they try to avoid the proximity of dogs. And by doing this, without realizing, they are driven to, to the gate that was located over there. So as you see, this was done computationally. We don't know how to analytically describe or at least pre-compute this. But once you see the simulation done, you say, oh, now I can explain it. Why? Because I see that these 4 dogs that are dancing in an oscillatory manner, they are building an invisible corridor along which sheep feel forced to move, right? Simply because they try to be at this geometric point in which the distance to the 4 dogs is maximized. And by doing this, they just get to the shelter. This is classical control theory, okay? So now the next video is deep learning. So this is a deep neural network classifying data according to the corresponding labels, in this case, the colors, 3 colors. And you say, well, this has nothing to do, although they look similar. I could have told you that maybe this was, again, on the right-hand side, a dynamical system for collective dynamics, where you have 3 different species, moving apart in order to be, according to some species selection principle or something like this, but not. So this is just deep learning. I have trained a neural network so to be able to classify data the same way we classify students at university depending on the different departments or different faculties. Okay, they look similar, but they belong to completely different fields. And actually, when you look to the video on the right, you say, well, of course, this is not control theory. Why? Because there are no dogs. No dogs on the right, no controls. So no controls, then it doesn't belong to the field of control theory. But now if you look in the book how this deep neural network is built, you realize that a lot of work has to be done offline a priori in order to what is called train parameters. And then when you simply think that training is computing, is approximating, is optimizing, and parameters is the same as control, you realize that the video on the right is also control theory, except that I didn't plot the controls, right? And actually, because this is a deep neural network with plenty of parameters, maybe if I have plotted the controls, then you will see simply a blurry image. Why? Because there are hundreds of parameters that have been pre-computed in order to succeed on doing this. But once you realize this video, then you see that the two fields are very close each other, and therefore you can, learn mutually, right? And this is therefore we did. So before we move forward, let me just, this is just a caricature, a very basic interpretation of an applied mathematician of how machine learning works. So I apologize. I know there are experts. Of course, you will say, oh, there is much more than that. Just let me just put it this way for those that were never exposed to machine learning, but know, already the principles of traditional applied mathematics, inspired in analysis and numerical analysis. So what you do in machine learning is you take a neural network. A neural network is just a graph. Nodes are called neurons. And then the difference between a classical linear graph and neural network is basically that every node has a nonlinear activation function, which mimics the functioning of the brain in the sense that each node, which is a neuron now, can be either on or off, right? So there is some nonlinear switch in each of these nodes that make this, in principle, linear, say, linear algebra model, a network, to become nonlinear. And then in every neuron, you have a few parameters in order to determine the intensity of the connections and whether this neuron is on or off. And then the only thing you do is you give me a data set, input, output, right? You give me a collection of data, like in the video to the right, so dots with colors, right? And then I try simply to find the neural network, the values of the parameters, so that whenever you give me an input X, then the output is very close to the corresponding label or output L. When you look to this, you say, well, but this is what Legendre and Gauss did, right? So, I mean, they did it 200 years ago. I'm sure if Gauss will see that now we call this machine learning, he will say, well, but this is what we called at that time least squares, right? The only difference is that for Legendre and Gauss, they were trying to do this also by the same optimization principle, right? As minimizing the quadratic loss plus some penalty parameter on the parameters to be trained. And that time they didn't use words like neural networks, they didn't use the word training, but this is what they were doing. For them, the model was just a linear function, right? Just the simplest possible. Nowadays, instead of considering linear functions, we can consider monsters as those employed in these large language models. But it's basically the same principle as least squares. So now you see that in this in particular, and this is something I want to emphasize, in the previous lecture, very interesting, by the way, all links through asymptotic analysis and multi-scale analysis, you have seen Schrodinger equations, equations in fluid mechanics, wave equations, aconal equations. So normally in applied math, we always use an equation with a name, right? Because the equation has to be adapted to the corresponding field of application. So here, it doesn't depend on the field. You just give me data, XL, input, output. I need to build a map linking X to L, and I always will do it using the same principle, just a neural network, a linear, say, network with the capacity of activating or turning off each of the neurons simultaneously. So the model is independent of the application. So this is precisely the opposite to whatever we have learned before. I mean, that was frustrating, right? When I realized in 2020 that everything I have, learned since I was a master's student in Paris was useless. Well, I was frustrated. I said, well, I have to start from scratch. But actually, that is not true, because in order to understand how things are working, it is true that from a modeling perspective, we don't use the classical equations in mechanics, like, Laplace, heat, waves, Schrodinger, and so on. But actually, the mathematics we will need are the same. Are the same except for the fact that now we are working in a giant dimension. So, you know, if you look to these videos, 3 blue, 1 brown, they are very well done in order to disseminate the basic principles of artificial intelligence and machine learning. They explain how in ChatGPT 3, in the free version, the number of parameters to be optimized is of the order of 175 billion. So 20 times the population of Earth, right? And I think in ChatGPT 4, the more professional version, you have to pay like $20 per month or so to use it. They are using even 1 trillion parameters. So the problem is, I mean, you could always say, well, 1 trillion parameter, it doesn't matter. This is RD, right? This is the Euclidean space. The dimension is just 1 trillion. So a continuous function on a compact set in 1 trillion space variables has a minimum and a maximum. So what is the point? I mean, what is the difficulty? Analytically, you know, there is no difficulty. There is a global minimum, there is a global maximum. The difficulty is that you have to find it, right? Because you have to tune all these parameters to make the neural network operate according to the databases you have learned. And you say, well, shouldn't be that long. You just take, you know, a piece of paper and you write on the left column the X, and then on the right column the L, and then they tell you yes, but please, you have to collect all the information on the internet. Oh, that's, you know, that will take, you know, more than one just sheet, right? Okay, so the course of dimensionality is there, huge dimension, and also, even though the problem look nicely convex, as in classical least squares, because the model of neural network is endowed of this nonlinearity that is turning on and off the neurons, the model is nonlinear, and as you know, the square of a nonlinear function is often non-convex. This is typically a non-convex optimization problem, and therefore the two evils are present, the course of dimensionality and the evil of the lack of convexity are making these problems extremely challenging, and this is why you need of the most powerful computers in order to tackle them. Now, what can an analyst do? Well, there are at least 3 questions you can ask yourself. The first one is, I mean, why all this is working so well? The second one is, can I use it for PDE approximation? The previous lecture of Yuan was already addressing this topic. And the third one, so maybe from a more applied perspective, we need to merge classical applied mathematics and machine learning, and this is what people working in digital twins are working on. So digital twins considered as being this field of science where data, mathematics, models, and decisions collide. And maybe for a PDE analyst, instead of talking about digital twins, I will simply coin the term PDE plus D, right? So it's just how you augment your PDE know-how and the use of PDE modeling and traditional applied mathematics by the fact that you have data available. Okay, let me then tell you very briefly my point of view about these 3 bullets, right? The first one is why this works. Well, actually, the fact why it works is already due to Norbert Wiener. Norbert Wiener, back in '33, Tauberian theorem, 100 pages in Annals of Mathematics. He initiated, at that time, he didn't use this terminology. That was a paper driven by Fourier analysis concepts and problems. But he already coined, somehow introduced the field of nonlinear approximation theory. What Wiener said, take a Gaussian profile like this, G, very much related to the previous talk. Take a Gaussian profile, and then if you let me doing translations of this Gaussian and then weights, B for translation and W for weights, then this generates a dense subspace of, say, L2 in a compact set, for instance. So every function can be approximated by these ansatz, in which the only thing you need is to choose the collocation of the Gaussians and then the weight you are allocating to each other. This is, of course, non-standard. It's not classical linear approximation theory as Fourier or polynomial approximation, because these parameters are entering non-linearly on the ansatz. Okay, so this was Wiener 33. We have to wait 56 years until Sibenko said in 89, this was published in a control journal, until Sibenko said, well, listen, what Wiener did with the Gaussian, I can do it with this sigmoid function. And people wanted this sigmoid function that has asymptote 0 at 1 because they wanted to mimic the behavior of the neurons. 0 is off, 1 is on, right? But in order to do that, Sibenko needed to use and introduce a new argument, the scaling factor on the variable x. His proof actually is based on Ham-Banach, right? Nowadays, there are much more constructive and quantitative proofs. His proof was based on Ham-Banach, simply using the fact that when you scale the sigmoid, then you get the Heaviside function. And then if there is a function that is orthogonal to all of them, then this function has to have the very property that, right? So question, what is the only function f so that on the real line, the integral vanishes to the left and to the right of any point? So what is the only function f defined on the real line so that the integral on every half line is equal to 0? What is the only function f so that the integral vanishes on every half line? It has to be the 0 one, right? Why? Well, because it's the only answer that is compatible with 0 everywhere. It has to be 0. But the reason for being 0 is that if you ask me, can you show that the function f vanishes at this point, for instance, I say yes. Because, you know, the function vanishes at this point because the integral over this small segment is 0. And the value here is just the limit of averages on small intervals. And why the integral over there is 0 is because the integral on this left half line is 0, and the integral on this half line is 0. And when I make the difference, I get the integral over there. That's all. Okay? That was the idea of the proof of Sibenko. In multi-D, there is more about this, but this is a very simple presentation in 1D. So people said, oh, but then this is fantastic. So because these functions are dense, then I don't need functional analysis. I can just burn all books, right? I don't need Sobolev and LP and Besov. I just forget about them. Wherever I am looking for a function, f, for any kind of application, I can just adopt this ansatz. And the only thing I need to know is how many neurons there are, and then choose the corresponding parameters optimally in order to fulfill the task. Okay? So later people realized that in fact you don't even need a sigmoid function with a sophisticated shape. You can take the classical, what is called the ReLU, rectified linear unit, which is the name given in machine learning to the function which is 0 to the left and linear to the right. That function is already able to determine whether you are 0 on the left or you are active to the right. This is the simplest switching function, which, by the way, is Lipschitz. And being Lipschitz is nice, right? Because, you know, this will be very useful in the context of dynamical systems. So this was the introduction to the theorem of universal approximation. Density is called theorem of universal approximation in this context. And this is how people, little by little, got to the point where you remove functional analysis and you adopt this kind of neural network ansatz and focus on just training the parameters to fulfill the corresponding task. Now, as I have said, these models become giant when facing real applications and large language models. Why we have some hope of being able to deal with very large dimensional systems with our limited human capabilities? Well, this is also rooted in another contribution by Wiener, cybernetics, when he said, cybernetics is the science of control and communication in animals and machines. 48. It took 10 years until Kalman wrote his celebrated result that says, listen, you give me a linear system, linear dynamical system, it can be a social network, it can be the WeChat network of the, I don't know, hundreds of participants in this conference. Can I guide, for instance, the opinion of all these individuals? Can I, for instance, bring them all simultaneously to the same room so to listen the same talk by just acting through some exterior control, some exterior input. So this could be, you could be the influencer, one or few influencers of a very large neural network, or sorry, a dynamical system, social network. What Kalman said, listen, it's not a matter of sizes or dimensions. I mean, in order to be an influencer, I mean, you can influence millions of people around. It's not a matter of how many influencers there are in order to guide a social network. The only thing you need to do is to make sure that this network is sufficiently connected and then be able to find the right message pointing in the right direction. And this is what Kalman said. Give me a system of dimension D. It doesn't matter whether the dimension is 2 or is 1 trillion. If the system has dimension D, and then the matrix B, it could be just a column vector, right? For one single influencer, a column vector B has the property that the rank of B, AB up to AD minus 1B is full, then the system is controllable. Means that this influencer will be able to choose the right strategy, UT, of input, so that the system simultaneously goes to the destination chosen. This theoretically, again, is very beautiful. Now, in practice, of course, this is something you don't want to do for a large system because you don't want to spend days or all your life just computing powers of the matrices and these rank conditions. So actually, you see that this field of artificial intelligence is also evolving in a way that we can benefit of in mathematics because, for instance, DeepMind is developing new tools inspired on reinforcement learning in order to multiply big matrices, which will allow us, for instance, to compute faster whether a system is controllable or not. But according to Kalman theorem, there is hope. There is hope that even if the system is very large, with just a few parameters, you can regulate the whole dynamics. And this is very useful in control theory, especially when you move from the original ansatz of Wiener and Sibenko to say, listen, what is this neural network? I mean, this is like a Shiba with many arms, right? You have k neurons, and there are 3 parameters in each neuron. So you have 3k parameters, and here you have to figure out just in one shot statically how to choose these 3k parameters. For me, it's very hard to figure out. But something I am used to do is to deal with dynamical systems, time discrete dynamical system, and then in every step, I can try to find out what are the best parameters I can introduce in this time step. And then instead of accumulating this neural network vertically, meaning that all parameters have to be computed simultaneously, I can do it gradually. And once I realize this, I say, oh, but this is just the time discretization of this differential equation. I will call this differential equation neural differential equation. And then the problem of driving data to the corresponding destinations will be just the same as the control problem I was considering before, except that now the nonlinearity will be present. The difference between Kalman and this model is that Kalman was linear, and this model is genuinely nonlinear because there is always a sigma activation function, for instance, the ReLU. But still, the ReLU is Lipschitz. The problem is well posed. And then the question is how to compute the parameters W, A, and B depending on time so that the system does the job. You see again this totally opposite perspective to classical continuum mechanics. The neural differential equation is always the same. And it doesn't matter whether you are dealing with chemistry, aeronautics, or heat propagation. It's always the same ODE. Okay? This is the magic of machine learning. Now, this works, and this is something you can see numerically. You just take this ODE, you fix this loss function to be minimized, you apply classical gradient descent or stochastic gradient descent to compute the parameters, you plot the output, and you see, well, it works, it does the job. So why? Why is this doing so well? The reason, and this is a paper we published with Domènech, a colleague in Barcelona, in Science Review back 2 years ago. I mean, this theorem is very long to formulate, but it's very easy to understand. So the theorem says, yes, we can. Right? So in dimensions 2 and higher, not in 1D. In 1D, don't ask me to classify data, because data, to be classified, they will have to collide, right? But if there is room, 2 and higher, you give me n data, you give me n destinations, I can always find, you know, parameter values depending on time, so that this neural differential equation becomes this fantastic Cauchy, you know, system, taking all the initial data to the corresponding destination. So this is like optimal transport, right, of mass, except that here I'm not claiming that I am doing optimal in the sense of Monge, but actually I am doing it with vector fields that are generated by this very simple, you know, neural network structure. The only thing I have to do is at any time try to determine what is the right choice for W, A, and B. Let me explain to you why it works. The reason why it works is basically the same as the Rubik Cube. So I'm sure there is people here that have solved the Rubik Cube. Did anyone ever solve a Rubik Cube? I'm sure. Did you? No. Who did solve a Rubik Cube here? I'm sure there is people. So nobody? You both won, right? Yeah. So, but we all know how it works, right? You take your two hands. With one hand, you fix half of the cube, and with the other, you know, the other half will rotate in a strategic direction. And then you concatenate motions until the Rubik Cube is solved, and we all know what that means to be solved. It means that all the micro faces of the same color are placed homogeneously on the big faces. So here is the same. Now, why the neural ODE is a perfect Rubik Cube solver? The reason is the following. Think, what is sigma? Sigma is 0 to the left, linear to the right. Now, take one of these points that is moving along this dynamical system, willing to go from the input to the output destination. Take one of these points, x of t. In which direction is x moving? Depends on the velocity. What is the velocity? The velocity is given by this. This depends on what? Well, on whether a dot x plus b is negative or positive. Whenever a dot x plus b is negative, sigma is 0, and this point is frozen. By the contrary, when a dot x plus b is positive, sigma is linear, and this is a linear ODE. The response is exponential, and this point is moving. And so now, what is a dot x plus b, positive or negative? This is just the two hemispheres you get when you cut a space into two halves according to the choice of the vector A, perpendicular direction, and the translation factor B. So with the one hand, on the right hand, I'm taking A and B, and every time I choose A and B depending on time, the only thing I'm doing is I'm cutting the Euclidean space into two halves. Those down are frozen. Those up are moving. And now the W is the direction of the wind. Well, direction of the wind wherever there is motion, wherever, you know, that are frozen, they are frozen. But on the active part where A dot x plus B is positive, the wind W is pushing you in the direction precisely of W. So you have two hands, A, B, and W. You cut and you push. You cut and you push. You cut and you push. And the claim is, if you do that smart, you succeed. What is the proof? The proof is by induction. And now you want to try to understand induction. You have to do it once. And once you realize that you can do it once, then you repeat. And because the number of data that you need to, you know, deal with is finite, maybe it's very large, this convinces you that you can control the system actually using controls that are piecewise constant with a finite number of switchings, which give you an idea of the depth of the neural network you need to employ in order to succeed. So in this very simple exercise, you see there are 9 data. 8 of them are well collocated according to the colors, but there is one that is badly collocated. The question is, how do you build the controls, right hand, left hand, so cut and push, so that the blue will go to the blue area while the others remain in the corresponding area. So you think a little bit, and you will easily find out that this can be done. Cut vertically, left frozen, right goes up. Cut horizontally, down frozen, up goes left. Cut horizontally, down moves to the left while up is frozen. Cut vertically, and that's all. Okay? So this is just one step in your induction argument. One motion? Two motions? Three motions? And four motions. Okay. Of course, there is much more, but this is an idea of why things actually can work and why classical control and dynamical systems perspective can help us understand why machine learning does some of the fantastic tasks is able to achieve so successfully. Now, if you try to think on how will I use neural networks for classical PDE approximation, then the idea comes immediately, right? The only thing you need to know is, this is the summary of all the existing theory of PDE, and this is the summary of all the existing theory for numerical analysis. If you know all PDEs and numerical analysis, then you will immediately come to the following idea, right? But let me tell you briefly. This was Hilbert. Hilbert said, listen, solving PDEs cannot be as complicated. It cannot be like for every PDE you compute explicitly the solution, the green kernel. I mean, green kernels can only be computed for very specific domains. That's not practical. He had the intuition that the solution of the Laplace problem have to be just the minimizer of the corresponding Dirichlet energy. At that time, he didn't know what the space should this be done on, right? It took some time to develop distribution theory and to find out Hilbert spaces, proper Hilbert spaces, Sobolev spaces like H10. Nowadays, this is elementary. A convex function, continuous coercive in a Hilbert space, has a global minimizer and is the solution of the Laplace equation, okay? So this is the modern theory of PDE. The modern theory of numerical analysis follows this idea and says, well, instead of minimizing over a Hilbert space of infinite dimension, let me just take finite element solutions, just take a grid, take piecewise linear continuous functions. There are finitely many of them. I mean, this is a finite dimensional subspace. I project this minimization problem, and then the minimum of this projected numerical analysis problem converges, and I have convergence guarantees of order 1. This is numerical analysis. Now, because we have learned about the theorem of universal approximation, we say, oh, now I'm merging PDEs and machine learning so that now you see what I'm going to do. Instead of minimizing the energy of Hilbert and Dirichlet in the Sobolev space H10 or in the finite dimensional linear subspace, I will do it under the ansatz, for instance, of Sibenko or Wiener. And then if I do this, of course, this will converge. But I'm introducing one difficulty, which is related to the fact that this manifold, the manifold associated to this ansatz is nonlinear, and therefore the problem becomes non-convex. Then I will be led with the problem of finding the minimizer of a non-convex function. So you see that as soon as you quit the classical theory of PDE and numerical analysis and you move into machine learning, you pay the tax of the lack of convexity. Now, people in the field have thought of this and said, well, but classically in control theory and optimization theory, whenever a problem is non-convex, what do? Well, you convexify it, right? So how do you convexify a neural network ansatz? By putting, instead of finitely many neurons, you put infinitely many, and then you make them denser and denser and denser until this sum becomes an integral. And when it becomes an integral, you say, oh, but now this is just an atomic example out of this more general ansatz in which I see this sigma now as a function of three variables, A, X, and B, that I'm integrating against a measure on A and B. What happens when I take a function sigma depending on A, X, and B, and I integrate it with respect to A and B? I get a function depending on X, of course. And what happens when this function, this measure mu is atomic, is just sitting in a few points, AJ and BJ, and has a given amplitude on each of these Dirac masses, WJ. You go from here to here. But what is the merit of this relaxation is that this relaxation now becomes linear on mu. And you say, oh, fantastic. So this was nonlinear. I have paid the tax of non-convexity. If I make it linear again, then I will be back to linear convex, and I will be happy. Yes, you will be happy, except that now you will have to minimize the Hilbert-Dirichlet energy over the space of measures, which is non-Hilbert, where the coercivity of this functional is hard to understand, so you will still have a difficulty. So you see why it's not that easy to integrate machine learning and classical PDE and numerical analysis in an optimal way. Why? Because when trying to use the strength of machine learning, you have to abandon the comfort of all the analysis we have developed to guarantee the success of classical numerical analysis and PDE theory. And then you encounter yourself in one of these Escher treppe in which, the gain is not clear and the direction of growth is not clear either. And this is where the last part of the talk comes. So given this difficulty here, the question is, what is the best way of integrating machine learning and classical applied mathematics? So what do we do? Well, it's very easy, right? So nowadays, when new students come to the team and they ask, they often ask, "Oh, professor, what should I learn?" I say it's very simple. In the old times, you have to learn what was differential equations with geometry and mechanics, was functional analysis, was partial differential equations, was numerical analysis, right? And then maybe optimization theory and control theory. That was all. Now, it's the same, except that you have to add the layer of data science, probabilities, statistics, machine learning, artificial intelligence, scientific programming. So, it's fantastic. The program is very ambitious, right? But then, in the past, the fellowships for a PhD were 4 years. Now they are 3 years, right? So now you have to do twice as much, but you only have 75% of the time. You say, well, how do you do it? Well, that's the challenge, right? Nobody said it would be easy, right? Okay, so now how do we integrate all this? It's not about abandoning classical applied math and hoping that machine learning will do everything. Neither is to say, oh, because this doesn't really work that well, because I'm losing the Hilbert structure and the coercivity of the functional, I abandon completely the idea that I should keep using machine learning. So what is the best way of doing? Well, again, the idea of the Rubik cube. You have two hands. You have to alternate one hand and the other, one hand and the other. How do we do it? Well, this is what we are developing now. It's something that you will do yourself if you had to do it. How? Let's see. Now, assume now I am in the modern paradigm where people have data. There are data coming from sensors. So how many attendees are in each of the rooms of the conference at every time? I have data, and I have measurements. T equals 0 black, T equals 1 blue, T equals 2 green, T equals 3 red, and so on. And I have to build a dynamical system that is interpolating this data. Can I do it? Yes, of course I can do it. Why? Well, because I learned the theorem before, that yes, we can, and as a mathematician, I like to repeat myself. So I do it again and again and again. And I can build a neural network gradually that will pass by all this data, just choosing in every jump from one color to the next what are the right parameters A, B, and W. And this can be done independent of the application. I don't mind whether this is a stock market or these are temperatures. I can always do that. Yeah, but people will say there is no physics on this. Okay, good. There is no physics on this. We should do better than that. This is just pure data-driven modeling. And our intuition is this cannot be sufficient because I cannot discriminate whether I am dealing with, hospital data about a given disease or stock markets in finances. This cannot be all. I need to inject, know-how coming from the field. How I do it? Well, our observation was, listen, to begin with, because we know, and this is the Pincus version of the theorem of Sivenko, who Pincus said, listen, what Sivenko said with the sigmoid, you can do it with every function, activation function sigma, except for the polynomials. The polynomials are bad. Except for the polynomials, you can do it with every function. Of course, you don't want to take here a quadratic function, for instance, a polynomial sigma. Why? Because wherever, independent of how many neurons you put and what the parameters are, what you get here is a quadratic function. So you don't escape from you get trapped as soon as sigma is a polynomial. Pincus said, except for this, all activation functions are nice. But this is the mathematical perspective. The practitioner perspective is to say, I don't need to deal with all sigmoid functions. I just take one, the ReLU, which is the simplest one to deal with, and I will work with it because I know I can do everything with that one. Now, our point was, listen, if you apply this theorem of universal approximation to any differential equation, then you are led to consider this very strict, limited class of differential equations, right? Because the vector field F can be approximated by the neural network, the ODE can be approximated by this, neural differential equation, in which you see there is some time dependency. The system is non-autonomous, but it's fantastic because the time dependency is even linear. So again, the only thing I have to do is add sufficiently number of neurons and then choose the parameters properly. And this is what we did. And this is a simulation that Sikian, who is sitting, he wants to show the poster. It's about this. Sikian Lee in our team. And we did this simulation for this classical model in atmospheric sciences, the Doswell frontogenesis model, which is a very beautiful explicit PDE in which you see this tornado that can be also computed explicitly, and this is a benchmark that is often used in order to test the accuracy of numerical solver, in particular in atmospheric sciences. You see how two fluids, cold air, hot air, start mixing according to this vortex and then develop an interface that is getting more and more complicated, and you really don't see the difference of the one generated by the model and the one generated by our numerical approximation procedure, in which what we say is, listen, if you give me sufficient sensors and you tell me how the direction of the wind is collocated in these sufficient sensors, then using these neural ideas, you can interpolate them and get a very accurate approximation of the tornado effect that Doswell represents. Now, moving forward, as I said, merging applied mathematics and machine learning is not about embedding PDEs into machine learning or embedding machine learning into PDE theory. It's rather using this idea of alternation, of splitting, that was coined in applied math already in the 19th century, right? So you have seen probably this logo, right? For those that don't know, just open it. You Google domain decomposition and you will find this domain. This is actually the logo of the domain decomposition community. Now you have books, encyclopedias, conferences, journals devoted to domain decomposition. But this is already explained in the book of Kur and Hilbert. This was developed by Schwarz in the late 19th century, 1880 or something like this. The problem that Schwarz had precisely before Hilbert was, and this is why Hilbert thought we have to switch the paradigm. Schwarz knew you can compute the eigenfunctions of the Laplacian on the disk, just radial coordinates. You can compute the eigenfunctions of the Laplacian on the rectangle, just separation of variables. Can I do it in this union of these two domains? Well, he could not, because the rectangle doesn't fit the radial coordinates. And on the other hand, the Cartesian coordinates are very bad for the circle. So what he thought was, so maybe then I have to do it in the circle, and then I use the interface information that this leads in order to later do it in the square, and then, alternate. So this is our proposal, and this is what, a paper in progress that will be soon released, hopefully next week. This is where we, implement this methodology. It's actually the one you will do yourself. You will devote some time to think on this, is to say, no, I'm not going to embed in a complicated manner machine learning into PDEs or PDEs into machine learning. I will keep PDEs as they stand, machine learning as it stands, and then alternate. so that whenever someone gives me data, I will feed the data to the synthetic model, right, the neural network, that I will train as is classical in machine learning. On the other hand, I will use the know-how I have from PDE theory and numerical analysis, right? Just with all the modeling, understanding we have of the different phenomena of nature, and then try to collapse, to hybridize these two modeling paradigms by doing what? By just trying to minimize the gap, right? Because when I minimize the gap between this machine learning model and this PDE model, what I'm doing? Well, I am pushing the PDE model to learn from data, and I am pushing also the machine learning model to learn from physics. They will reach some, Nash equilibrium. You don't expect them to coincide because they represent two different worlds, but they will get very close, and this will be the point in which you will stop your training process, because you will have reached to that level in which the PDE can absorb the data as well as they can, and on the other hand, the synthetic model, which is rigid because it's given by this neural network architecture you have imposed a priori, will have learned from PDEs as much as possible. And this will be the new hybrid cooperative modeling strategy that we propose. And with this, I will just to thank again the conference for giving me the opportunity to be here, to also learn about BIMSA, even from locals, and invite you all to think on this. So, well, I mean, you can take your time. You don't need to do it on the rush, right? So, but from each of the classical fields in mathematics, and in particular in applied math, understood in a broad sense, there is plenty to do in this direction. Doesn't really matter whether you are an analyst doing approximation theory or Fourier analysis, or you are a probabilist, or you are a numerical analyst. I'm sure you will find fantastic topics to think of. And you have the two different avenues, right? So you have the math perspective. This is the one we like the more, right? So think on questions like, the minimal complexity of architectures, the generalization properties, links with probabilities. Of course, nowadays, large language models use a lot the attention mechanism. There is this celebrated paper, attention is all you need, right? And basically, the way I explain the role of attention in all this is that, attention mechanism allow you to pack data. And when you pack data very well, this allows you to classify data in a faster manner, using less neurons, less switchings, right? And this has been the breakthrough that led to, to this large language model, which of course is very much related to classical approximation theory, Johnson, Linde, Strauss, to the concentration of measure, and many other phenomena that are well known in functional analysis and probabilities. And then there is the more applied perspective of really, contributing to develop this new emerging field that I bet soon will be a session in MassCNet, right? You will have soon not only the classical ones, including PDE, but you will have also PDE plus D, right? Which is the mathematical interpretation of what digital twins should be, which is this, new, computing laboratories in which you will have the possibility of integrating data in a real-time manner thanks to, the tools of artificial intelligence, and combine classical control theory, not only to integrate the data, but to manipulate the data and decision-making in an optimal manner. Thank you again. Thank you.
Thank you for the great talk. I have a question. Do you use specific networks to merge PDEs with machine learning, or you devise your own?
No, I mean, in this paper we are writing, we test different possible paradigms, but you can use the classical, say, one layer convolutional neural network. So here there is plenty of freedom, right? And of course, I mean, you can do better by employing, neural networks that are, like this Kolmogorov, Arnold, and so on. Of course, you can increase the complexity of this model, but always keeping in mind, because, something we observe by writing this paper is that in the beginning we were using very complicated neural network architectures, and we were observing the numerical simulations. And then I asked to my colleagues, Lorenzo and Thijs, I asked them, did you try doing it with a much simpler neural network architecture? And then they try, and you see what happens? You basically get the same. So keep in mind always the Occam razor, principle. In all these contexts, it is not worth to go from the very beginning into the more complicated neural network architecture, just to start from scratch, except if the problem is of such a big magnitude that you have to really employ a large language model. And then try to understand how this cooperative methodology works before you escalate into more sophisticated architectures. But do it gradually, because probably you will find a very, satisfactory answer by not using that complex neural network architectures.
Thank you.
Thanks.
You were putting the example of left hand, right hand for this. So there is this Bible saying that, do you know what your left hand does, or blah, blah. So my question is, like in this cooperation with for instance, you put the example of DeepMind, no?
Mm-hmm.
Do you know what's in, how do they do it? I mean, is there a way?
Well,
What is like, can we, because in this principle idea that you said at the end, we would be able also to interact, and this means that we need to know the rules of the game. Do we know that?
So there is this famous saying of, I think it's called the bitter lesson by Shatton, right? The bitter lesson by Shatton says, Rich Shatton, one of the, of the founders of this field of artificial intelligence, basically he said 5 years ago, this is the bitter lesson, you can find it easily in the Wikipedia. He said, well, we did so much effort. As we mathematicians do. Basically, the way I understand it, not being an expert, is I think they were really trying to say, how should I train a neural network? How the parameters should be chosen optimally? And they never were able to do it. Why? Because in the end, eventually, the problem has to be solved by a supercomputer. So what finally mathematicians, scientists in this field realized that the way to proceed was to adopt a sufficiently large architecture and let the computer find the optimal solution. And this is very much consistent with the classical practice of numerical analysis. In numerical analysis, we say, okay, take this PDE, do finite differences or finite elements or finite volumes, but let the computer compute. The mathematician will never be able to compute the solution numerically, analytically. You have to let the computer do it. The computation, and here you also know the rules, right? The rules are, this is the architecture, and this is the functional you are minimizing, and the only thing you say to the computer is employ a stochastic gradient descent method, which is nothing than, geometric descent and a bit of randomization. These are the rules of the game.
Yeah, but if you go to a private company, this is my question. You don't know all the rules. So it's
but also, when you buy Comsol, one of these classical finite element solvers for industry, well, you don't know the rules either, right? So this is finite element theory, but how they do it, why this does better than this other solver for, corrosion problems, you don't know. Why? Because they invested plenty of money on having something that they don't want to share. They wanted, industry operates, but you see, this is inevitable in some sense, right? So that was a colleague in Bilbao who was, I think, the leader of Facebook Facebook or so, one of these big companies in Spain for a while. He told me, Javier Echeveste is his name. He lives next to me in Bilbao. He told me, Enrique, we in industry, we do the opposite to what you do in academia. In academia, when you discover something, you want to share it with the others. In industry, when you discover something, you keep it for you. But somehow we know what the rules are, the general rules. And other than the difficulty that, of course, industry will always preserve privacy and confidentiality in order to have a competitive advantage, there is something that is more challenging for us. And I think it's the fact that we are dealing with these two monsters, right? High dimension and the lack of convexity. And our human intuition really fails, right? So, you know, I understand 3 dimensions. For the 4th dimension, I need a watch. But then from 4 dimensions to 1 trillion dimensions, there is a gap, right? This is the gap to fill. And this is the bitter lesson. Unfortunately, we are humans, and we cannot understand that. But when we let the computers evolve in these high-dimensional spaces by using these elementary rules, you find tools as ChatGPT, which are extraordinary. You know, giving this talk often among experts, people ask me, where did you find the paper of Wiener? Nobody quotes Wiener. For people, the theorem of universal approximation starts with Sivenko. How do you think I found Wiener? As a non-expert, asking ChatGPT again and again about the principle, the foundations, the roots, the original ideas and contributions in ChatGPT, until I found the paper of Wiener. So welcome to the new world. Thank you.
Okay, thank you for attending this afternoon session. We're going to have to move the questions to offline discussion.